All right, good morning. So today, some of you guys have already tested. So if you've tested, this is still information from um, our unit 1, but these are some of the things that I haven't really talked about and you guys do still struggle with. And of course, building a good foundation now, we'll see a lot of this stuff pop up again throughout the semester. So let's make sure that you guys understand it. Next week, I will be going into the next unit. So if you're on task or ahead, like hopefully I'll get some information that you guys haven't seen yet. Let's go ahead and make this a little bit more focused. This thing's very finicky. Oh, come on, be our friend today. There we go. All right, so we're going to start off with an example of literal equations. Now, when we talk about a literal equation, it's just like our basic algebra when we're solving for that variable, but sometimes when we get a bunch of different variables, it really throws us off. So we always want to make sure that we know what are we looking for. So I'm looking for W, which is this variable right here. So all I want to do is get it by itself. And so what we often do is we do our reverse order of operations to get it by itself. So normally we add and subtract, multiply, then divide. But when we talk about doing this, we want to do our reverse order of operations. So just as a little bit of reminder, what is our order of operations? So our order of operations. So our order of operations is parentheses, exponents, multiply, divide, add, subtract. Okay, so when we talk about this, again, we want to focus on order of operations. And often, this happens quite often, is that there's more than one way to get to the same answer in math. There's not always just, hey, this is the only way to do it. You can get the same answer and do it totally differently than me and still be mathematically correct. So think about that as well. If you get a different answer, doesn't mean that you did it, or sorry, get the same answer, but you did it a different way, does not mean that you didn't do it correctly. All right, so again, my goal is to get my W by itself. So first thing that I'm going to do here is I'm going to do what I call cross multiply. If I have two fractions, two ratios set equal to each other, and this again is super finicky. So let's see if we can get that to work better. Set two ratios set equal to each other, or two fractions set equal to each other. I like to cross multiply. And when I cross multiply, I end up with y times my W plus 2 is equal to 2z. So that's just to show that it's a z versus a 2. Sometimes when I write it, they look alike. Times my 2x minus 1. All right, so from here, I can look at this as two different ways. Again, I'm trying to solve for my W. So my way number one could be where I go ahead and I distribute this y to each piece, this 2z to each piece. This camera is very terrible. So when I do that, I get yw plus 2y is equal to it's going to be 2 times 2 is 4xz minus 2z. So some of you guys go, is it xz or zx? It really doesn't matter. Often we do alphabetical order. So if you did zx, it's not wrong. Remember, it's just saying 4 times x times z, or 4 times z times x, and it's equivalent. So again, I'm looking to get this w by itself. So I need to get rid of this 2y. There's no like terms there, so I can only combine if these are both z's. That's the only time I can combine it. So there's no like terms. So I end up with yw is equal to 4xz minus 2z minus 2y. And then I would do my last thing is I'm going to divide everything by my value of y, because I want to get the w by itself. So we end up with w is equal to 4xz minus 2z minus 2y all over y. That's one way to write it. Or if I wanted to, I could break these apart so that I ended up with 4xz minus 2z all over my y. And this, instead of it being written like this, it would be the same thing as negative 2y all over y, but those would cancel out, right? So it'd be just minus 2. So these two equations here are equivalent, and your answer could have been written either way. They're exactly equivalent. Another way I could have solved this, so here we went ahead and we distributed those coefficients through. Another way I could have solved this is if I was looking for this w, I need to get rid of this y, so I could divide it by y right away. And if I did that, these y's would have canceled out, and I would have been left with w plus 2 is equal to 2z 2x minus y, minus 1 all over y. And then I could have just subtracted my 2 from here. So that w was going to equal 2z times the quantity of 2x minus 1 all over y minus 2, which is, again, the same thing as what we have over here, just another way. So the 2z is factored out here. So all three of these are going to be the same. All three of these answers are all equivalent. This is equivalent to this, which is equivalent to this. Hi, Madison. Thanks for joining. I'm just going over some problems. If you have a particular question, please let me know. So I have one more example planned out. And then again, if there's anything else you guys want me to go over, just make sure to let me know. All right. So that was an example of a literal equation. Sometimes we're given like, hey, which ones of these are equivalent? So you might have to distribute things to simplify and work it out that way. But again, all of these are equivalent answers. You just matter of how you're given your answer. All right, my next one is quadratic equations. And so this is going to be an inequality. So we talk about the shading for this. So remember, if we're asked to determine the solution, we want to solve for x. So we're looking for x. We want to know, what can x be? Something I want to make sure to point out is that when we use these problems, we want to make sure that it's set equal to 0. In this case, I shouldn't say equal to, greater than, less than, equal to 0, so that you have all of your values, your real numbers, as well as your variables all to one side whenever we do this. So we want to make sure to set equal to, or you could do less than equal to, greater than equal to, or strictly just greater than, or strictly just less than to 0. If that's the case, as long as it's going to be where you have your 0 by itself, then if you have a greater than or a greater than or equal to, it's what we call a GOR statement. So if my 0 is going to be on my right side, this is only true if my 0 is on my right side. If it's greater than or greater than or equal to, it's what we call a GOR statement, which means it's an OR. So this or this can happen. If it's going to be less than or equal to 0, if it's going to be less than, then we say it's a LAND statement to kind of help us remember. In other words, it's going to be an AND. So it's either a GOR or a LAND. So or and. So what's the difference? When we have an or, it's going to be this or this. So it has to have two separate pieces. When it's an and, it's just going to be one set. It's one set because it's everything that's in between it. So an or would be something that's going to look like this. Our ands would be something that go like this. So just from looking at this, because it is a greater than or equal to sign here, I know that it is going to be an or statement. I know without even doing any work, it's going to be an or statement. So I'm going to solve this two ways. I'm going to solve it graphically, and I'll go ahead and solve it using the calculator. So you can see, you can choose whatever way you want. I'm not babysitting you. You don't have to do it a certain way. So whatever way you feel is easier for you to read, interpret, and use, then go for it. So if I was going to solve this graphically, I would start off by factoring. So I like to use the magic X. So when I factor this, I need two numbers. So my outer numbers multiplied to a negative 28. My inner numbers are going to is the value of negative 3. So I need two numbers that multiply to negative 28 and add to a negative 3. So those two numbers are going to be negative 7 and 4. These are going to be what I use to write my factors. So I would have x minus 7 and x plus 4. It's still going to be greater than or equal to 0. This is just a factored form. The reason why I do this is because this helps to give me what we call our critical points. So vocabulary, our critical points. Our critical points are the values that we get when we set these equal to 0. So if I set x minus 7 equal to 0, then I would have x is equal to 7. In this case, if I set x plus 4 equal to 0, I would have x is equal to negative 4. These again are our critical points. And those are the points that we use when we create our number line. This number line basically represents our x-axis. So I have a point here at negative 4 and at 7. So these again, these values are because these are my critical points. So I want to figure out then, again, I already know it's an or because of our little trick here. So I know that my graph is going to be solid points here because it's equal to. If it wasn't equal to, it'd be an open circle. And they're going to go in opposite directions because it's an or. But I want to verify that. How do I know that's actually true besides the fact that I said, hey, if you have it written like this, it's going to be the case. So let's go ahead and look at how I know. Well, what if I pick a point that's going to be to the left of negative 4, such as negative 5, and I plug it in here? So negative 5 minus 7 is going to give me negative 12. Negative 5 plus 4 is going to give me negative 1. A negative and a negative are going to give me a positive, right? I don't even care what the number is, but I know it's going to be a positive, right? So if it's a positive value, it's greater than or equal to 0, right? So this is true. Since it's true, it's part of the solution. Since it's true, this would be part of the solution. So I'm going to highlight that. Shade it. If I pick something such as 0 here, 0 minus 7 is negative 7. 0 plus 4 is going to be 4. When I multiply these numbers together, I don't really care what the number is, but I know it's going to be a negative, right? Since it's a negative, it's going to be a negative. Is that greater than 0? No, can't be. So this is not true. So it can't be part of the solution. See how I don't have it shaded up there? It's not part of my solution. And my last little piece over here, if I pick a number such as 8, I could have picked 1,000, any number. I'm just picking numbers that are easy to work with. So if I plug in 8 minus 7 is going to give me 1. 8 plus 4 is going to give me 12. And I'm going to go ahead and I'm going to have a positive number, which a positive number is going to be greater than 0. So I'm perfect that this is true, which means this is part of my solution set as well. So this is part of my solution. This is part of my solution. And we had already said that was going to be the case. But what I didn't do yet is actually write out my solution. What does that look like? Well, here's the piece we're missing. So if I say that these are my solution, what does that look like? So it would be this, I would say, since it's pointing to negative infinity, I would say negative infinity to negative 4. And it's going to be this type of bracket. This bracket right here means it includes it. If I use this bracket right here, that means it would be an open circle and it would be everything up until negative 4, but it does not include negative 4. When it's an equal to, we have to use this bracket. So it's going to be negative infinity to negative 4, or we're going to have 7 to positive infinity. And this is what our solution set would look like. There's our solution set. I'm going to go ahead. I'm going to share another screen with you guys really quick because I want to show you guys how do I do this if it's going to be something, if we're going to do something on the calculator. Can you guys see me on the searching for a Desmos right now? Make sure I showed the right screen. I don't know if you guys can see what you guys are seeing. Are you guys seeing me do the calculator? Perfect. Okay, so I'm just plugging in same equation I had. It was going to be X. So I just Googled Desmos. You could go into your Edgenuity and do it as well. I actually preferred the online version than the one that's in Edgenuity. So it was X squared minus 3X minus 28 is going to be greater than or equal to 0. Nope. Let's put that in. So you can see right here my values. So you can see here's my -4. Oh, and I did my inequality. It's greater than. So here's my -4, and here is my 7. So when I look here, you can see that in between those two, it's not shaded. So I'm going to go ahead. I'm going to share my paper because I'm going to point out the important information, but this is where I'm getting it from, is from that calculator there. So when I go back to my paper over here, just like we did here, this is I said represents my x-axis. We're focusing in on those x values. Our solutions are the x values. So when I had my graph that we just graphed, this was going to be -4. This was going to be my value of 7. So everything over everything over here was shaded. I don't even care about anything else other than where I'm at on my x-axis. It's only my x-axis that I care about because I'm looking for my x values, the solutions for the x values. So again, we want to look at our x-axis. So if that's the case, again, it was going to be a solid line through here. So it's going to include that point, and it was everything going to my negative infinity. And again, it was a solid line through 7. So it includes that point and everything going to my positive infinity to get my same solution set. So again, you guys have two different ways you could have looked at it. Two different ways. Those are the only two problems I have set up for today. Are there any other particular questions or anything you guys would like me to go over?
No, ma'am. Everything's all good. Everything's
Awesome.
understandable.
Awesome. Well, thank you. I'm going to go ahead. I'm going to stop the recording.